Welcome to the Introduction to Correlated Materials, a series of lectures to help you understand and admire the role of electron-electron interactions in solids. Brought to you by Schrodinger's Kittens Productions. Lecture 4, the Hubbard Hamiltonian. In this lecture, we'll quantify the Mott-Hubbard phase transition that we introduced qualitatively in the previous lecture by writing down explicitly the Hubbard Hamiltonian, which is the simplest possible Hamiltonian or the simplest possible model Hamiltonian. That captures the physics of the Mott transition. I want to start, though, by introducing some new notation, or reviewing some notation, for those of you who are already familiar with it, which is called second-quantised notation. And in second-quantized notation, we work in terms of operators, the first of which is called the creation operator, and it has the symbol C, subscript I sigma, and superscript dagger. And what this operator does is that it creates an electron on site or orbital I with spin sigma. Sigma can be, for example, upspin or downspin. The second operator we'll be working with is the annihilation operator. And this has the symbol C sub I sigma. And this operator kind of obviously annihilates an electron on site or orbital I. Again, with spin sigma. For the case of electrons, which obey Fermi statistics, we know we can't have two electrons on the same site with the same spin. And so we can write down immediately that if I try to annihilate twice an electron on site I with spin sigma, then I'm always going to get a zero because there can never have been two electrons on site I with spin sigma. So C sub I sigma squared, the operation of applying the annihilation operator twice, will always return a zero. And likewise, if I try to create an electron twice on the same site with the same spin, I will also get a 0 because I can never create two electrons on the same site with the same spin. So just a little bit more complicated. Let's think about what does the operator C sub I sigma dagger C sub I sigma do when I operate on a wave function. Well, when I apply C sub I sigma dagger C sub I sigma to any wave function, the first thing that I do is I annihilate an electron on site I with spin sigma, and then I create an electron on site I with spin sigma. And so this operator will count whether there is an electron of spin sigma on site I, in which case it will return a 1, it'll annihilate that electron and then create it again, or not, in which case it will return a 0. So for example, let's write down some general wave function which has an electron sitting on site I, and I operate on it with C sub I sigma dagger C sub I sigma. Then the C sub I sigma will destroy this electron on site I, giving me C sub I sigma dagger operating on a state that has no electron on site I. And then the C sub I sigma dagger will create this electron again. So I'll end up exactly back where I started. And the effect of operating, or the eigenvalue for this operator will be just 1 in this case. If there had been no electron on site I to start with, then immediately the C sub I sigma would have tried to annihilate a nothing, and I'd have ended up with a 0. So because of this property of counting, we call this operator the number operator. And it's usually written as n sub I sigma is equal to C sub I sigma dagger C sub I sigma. Okay, let's go one more complicated again. So what about the operator C sub I sigma dagger C sub j sigma? What does this operator do? Well, this one we can see annihilates an electron with spin sigma on site j and creates an electron with spin sigma on site I. So this operator takes an electron with spin sigma from site j and moves it, it puts it on site I with the same spin. We have this new notation that actually gives us a nice way a nice notation for writing down the linear combination of atomic orbitals, Hamiltonian, that we reviewed in the very first lecture in this series. At the moment, when we write this down, it's going to not seem a very useful way of writing it down, but we'll see that when we extend it to the Hubbard Hamiltonian, it will be very convenient. So our Lcao Hamiltonian in this notation, remember the first term in the Lcao energy is the energy for an electron sitting in an atomic orbital on a particular site, on a particular atom. And in this notation, we write this as alpha, the sum over all the sites and over all the spins, times our number operator. An electron will contribute an energy if it's there, and it won't contribute an energy if it's not. And here, our alpha term is, in real space, the integral of the wave function for the electron on site I, complex conjugated, times the Hamiltonian, times the wave function for the electron on site I, dV. So these are the terms in our Hamiltonian matrix that have I is equal to J. And in the second contribution to the Lcao Hamiltonian were the terms where the electron transferred from one site to the nearest neighbor site. And in our new notation, we write that as plus beta, the sum over all pairs of nearest neighbors, and again over all spins. And in this notation, we create on site I the electron that we've annihilated from site J. And then we also, of course, include the complex conjugate so that our matrix is Hermitian. And our term beta in this case is the integral of the complex conjugate of the wave function on site I times h times the wave function on site j. So the first set of terms are the terms with I is equal to j, and the second set of terms are with I and j equal or nearest neighbors. And this bracket here means that our summation is over I and j being nearest neighbors. Now, at the moment, this might seem just a bit of a complicated way of writing down what was much more straightforward when we looked at it in real space. But when we next explicitly include the electron-electron interactions, then we'll see that there's a definite advantage to this notation. So let's do that next, and we'll include electron-electron interactions at the level of the Mott Hubbard picture. So we'll include the Coulomb interaction between two electrons on the same site. The same site or orbital, if you prefer to think in an atomic orbital picture. And this we can write down very straightforwardly It's repulsive, so it's positive. You usually give its magnitude by U. We have to sum over all the sites, and the number of electrons on site I is just given by the number operator. The number of electrons with spin up is n sub I upspin. And of course, the other electron on site I that can have a Coulomb interaction with the upspin electron has to be the downspin electron. And the number of downspin electrons on site I is n sub I downspin. So this is our Coulomb repulsion between two electrons. They have to have opposite of spin if they're both occupying site I. And of course, if either the upspin electron is absent or the downspin electron is absent, then this term goes to zero because there can be no Coulomb repulsion if there's only one electron. One thing I forgot to mention when we wrote down the Lcao Hamiltonian is that the beta term here is negative. It's kinetic energy lowering because it allows the electrons to transfer between adjacent sites. Beta term is negative. Whereas, of course, the U term, the Coulomb repulsion, is positive. It increases the energy of the system. So this has a very simple form. The Coulomb repulsion between two electrons is a very simple form and is the reason that we tend to use second quantized notation in systems where we want to explicitly describe the electron-electron interaction. Okay, so let's summarize all of that then. So the Hubbard Hamiltonian is usually written in the following form. Instead of beta, we usually write minus T, where T is just minus beta, obviously, to explicitly indicate that this is a negative quantity, that it's energy lowering. Sum over the nearest neighbors and the spins. C sub I sigma dagger, C sub j sigma, plus C sub j sigma dagger, C sub I sigma, plus, exactly as we wrote before, U times the sum over all the sites, n sub I up times n sub I downspin. And usually the alpha term, the term representing the energy of the electron sitting on its own in the atomic orbital, is usually left out because all that does is shift the zero of energy, and so it's not considered to be important. Okay, so now we have a Hamiltonian. It's the simplest possible Hamiltonian that will describe the Mott transition. It's just the simple linear combination of atomic orbitals Hamiltonian, plus this extra term describing the interaction of two electrons sitting on the same site, the same orbital of the same atom. It's a model Hamiltonian. It looks rather simple, but in general, it cannot be solved exactly, and so approximations have to be made. And so let's look at the solutions at different levels of approximation and see if it really gives us a Mott transition. Okay, so let's look at the solutions of the Hubbard Hamiltonian in various limits. So the first limit I want to look at is the non-interacting limit where u is equal to 0. And in this limit, of course, we regain the linear combination of atomic orbitals theory, and we can write down an exact solution. And so if we look, for example, at the density of states as a function of the energy for an array of orbitals, each containing one atom, then we get our usual form for the density of states from our Lcao theory, where we get a band that's half filled because each atom contributes 2 possible states, an up and down spin electron, and only 1 electron. And so we have a band which is half filled, and our system is a metal. If we look at the fully atomic limit, in this limit, T is equal to 0, there's no bandwidth, and our density of states, it's not really a density of states, it's just a series of discrete energy levels. It's a function of energy. It has just 2 peaks. That are separated by U. The lower peak takes 1 electron on each atom. The second electron is separated from that in energy by the Coulomb repulsion, and so our system is insulating. In between these 2 limits, again, it's not possible to solve exactly or to analytically to solve the Hubbard model. But what I'm showing on the right here is a numerical solution made in this paper here using a technique called dynamical mean field theory. Which is a numerical technique. Again, it still has some approximations, but it allows at least an approximate function of the Hubbard Hamiltonian. And this series of plots, these are all showing the density of states as a function of energy. It's written energy or frequency. These plots are showing how the solution, how the density of state solution evolves as a function of the ratio between the Coulomb repulsion U and the bandwidth T. So in the top plot, U is equal to 1, U is equal to 2, U is actually equal to 2.7, U is equal to 3, and U is equal to 4. And all of these are in units of relative to T is equal to 1. And the Fermi energy is set to be 0. In the middle of the plot here. And here we see a gradual evolution from a density of states that looks very like the non-interacting limit at small u, to the atomic limit with two separate peaks separated by a gap, as a function of the ratio of the Coulomb repulsion to the bandwidth. Next time we'll move beyond this model picture and actually look at some real materials that are described by this physics. Thanks for listening.